Good morning class and welcome to our continuing lectures on sustainable energy technology. In the previous class, we began our discussion on thermal energy storage systems. So in these discussions, we are looking into technologies that help us store thermal energy in terms of temperature gradients or latent heat storage systems. We discussed storage technology related to latent heat storage, where we use a high density material with large volumetric storage density like packed brick structures, which are heated up in times of low electrical energy demand, and this heat is then used to heat up water or air systems that go into buildings. Next up, we had started our discussion on latent heat based energy storage systems, which are usually used for high temperature applications where industrial process heat is needed at a high constant temperature, or where we need to use that heat to generate electricity. Latent heat is basically heat that is absorbed or released when the material changes its phase from, say, liquid to vapor, as in the case of water, to steam, or from solid to liquid, as is the case of molten salts, molten metal, etc. So when the latent heat based phase change energy storage material is being charged, it is absorbing heat from an external source, and that heat is being transformed into latent heat of phase change, as it is changing its phase from liquid to vapor or solid to liquid. Then during the discharging phase, it is releasing heat at the same constant temperature of solidification or condensation. And as it is releasing this heat, it is changing its phase back to its original phase, which is liquid for water or solid for metals or salts. Okay. And we looked at certain types of phase change materials that work in our cases, like pressurized steam, other types of pressurized vapors, molten metals, molten salts, etc. And thermal energy in these cases is released at a constant and controlled temperature. These are ideal where heat and constant temperature and pressure is needed. Example, industrial process heating and power generation. And the amount of stored latent heat is usually much greater than stored sensible heat. So you are able to store the heat to a much larger extent at a controlled temperature, which makes it ideal for industrial and power generation applications. So for example, sensible heat released by liquid water as it cools from 100 degrees centigrade to 27 degrees centigrade is 322 kilojoules per kg. So if you look at liquid water, which is at 100 degrees, just about to boil, and cool it down to room temperature, say 27 degrees centigrade, then the heat that you are releasing per kg of that water is 322 kilojoules. In contrast, latent heat released by steam at 1 atmosphere pressure as it condenses to liquid water is 2257 kilojoules per kg. Okay, so we see this is more than 8 times that of what can be released by sensible heat alone. So 1 kg of steam at 100 degrees centigrade releases 2257 kilojoules of heat as it condenses back into liquid water at 100 degrees centigrade. Latent heat storage is a good way for steam power plants to cater to variations in energy demand. So during period of low demand, excess steam from boilers is diverted to large insulated pressure vessels called steam accumulators. At periods of high demand, this stored steam is diverted back to the steam turbine to generate additional power. So this strategy of storing extra steam when the demand from the grid is low and then using that steam to get additional power when the demand is high helps to match the demand supply cycle of a grid with your steam power plant. Okay, this steam power plant may be related to a nuclear power generation system, a hydrothermal power generation system, a traditional coal power generation system, or a biomass based power generation system. Okay, so in any of these cases, if you want to make it possible that the steam power plant is increasing its electricity supply when the demand from grid is high and lowering its electricity supply when the demand from the grid is low, use storing steam during times of low demand in these accumulators and using that steam to generate excess electricity during periods of high demand is a good economic way of demand supply matching. Now, while steam is an excellent and widely available medium for latent heat storage, it cannot store heat much above 300 degrees centigrade, where its boiling point pressure rises to 9 megapascals. So remember, 1 atmosphere is 0.1 megapascals. Okay, so 9 megapascals is around 90 times that of the standard atmosphere. Okay, so this is 90 atmospheres almost. Okay. And the latent heat of vaporization falls to 1400 kilojoules per kg. Okay, so this is because of the vapor dome of water. Okay, so this is the liquid side, this is the steam side, and this is the two-phase zone. Okay, greater is the distance between the liquid side and the steam side at a given pressure, greater is the latent heat of evaporation or the latent heat of condensation that is available during the phase change process. Now, as the pressure increases and the temperature increases, the two liquid side and the vapor side converges on each other till the critical point, which is 374 degrees and 22 megapascals, when you are getting supercritical steam where there is no discernible phase change process happening and the entire fluid is in a supercritical state. We will not discuss this here. The basic idea is, as you increase the pressure and the associated boiling point temperature of water, the latent heat of vaporization drops, and at 9 megapascal it has already dropped to 1400 kilojoules per kg, which, if you remember, is significantly lower than what the latent heat of vaporization is at 1 atmosphere pressure. Okay, so now we pressurize steam in order to make it work in a steam turbine power plant and to increase the temperature at which this steam is getting converted back into liquid water. So at 9 megapascals, the boiling point temperature has risen to 300 degrees centigrade from 100 degrees centigrade. But on the flip side, your temperature, latent heat of vaporization has fallen. So there is a price to be paid of increasing this temperature, and we cannot increase the steam temperature much above 300 degrees centigrade. So what this means is, for those applications where you need temperatures higher than 300 degrees centigrade, steam is not a good energy storage medium. So in order to store heat at higher temperatures, phase change materials like molten salts are used. So here we are switching from a water-based phase change system to a salt-based phase change system. The phase change process for molten salts, solid to liquid transition, happens at around 600 to 850 degrees centigrade. So significantly higher temperatures. So depending on the salt composition, the temperature may vary. It's around 600 C to 850 C. And the specific thermal energy of storage is 1000 kilojoules per kg. So you are getting, for 1 kg of salt, around 1000 kilojoules of heat is absorbed or released during the liquefaction or the solidification process. Hence, good power generation efficiency is obtained. Because remember, to increase the efficiency of power generation, you need to increase the temperature of the heat source. Higher the temperature, greater is the potential energy of power generation. And molten salts can double or triple the temperature of the system from a water-based system. And its thermal storage, specific thermal energy storage is also quite good. Not as high as water at 1 atmosphere, but at these high temperatures with reasonably good thermal energy storage, molten salts become a very good phase change material. Further, since salts are in liquid form and are not gaseous like steam, the volumetric energy storage capacity is quite high. So the entire requirement of compressing the steam is not there. Okay, so that of course, and hence you have a larger volumetric heat storage capacity, because liquid salt is much denser than even compressed steam. So you are saving the energy required to compress the steam firstly, and because it's a significantly denser liquid than a gas, your volumetric energy storage capacity is quite high. So the latent heat on a volumetric basis for molten salts is 1670 to 3770 kilojoules per meter cube, which are much higher than that of steam, 1670 to 3770. Okay. Typical salts include sodium nitrate NaNO3, potassium nitrate KNO3, and sodium nitrite NaNO2. Okay. So these salts are typically used as molten salt based phase change materials for latent heat energy storage systems. So this molten salt based technology is often used in nuclear power plants and concentrated solar power plants where high temperatures can be achieved. So if you remember the concentrated solar thermal power plants, you are focusing all the sunlight into a small area, those radial concentrated solar power systems, and you are getting very high temperatures. So you need to preserve that high temperature to improve the efficiency of your electricity generation system, and molten salts by melting at 600 to 800 degrees centigrade is the ideal medium which can absorb this heat at a very high temperature and release this heat at a high temperature as well to increase the efficiency of your overall system. Similarly, nuclear power plants also run at significantly high temperature compared to traditional power plants, and there also molten salt based energy storage systems are very useful. Now the main drawback of all thermal energy storage systems is heat loss. Okay, heat loss is inevitable. Regardless of the insulation you are using, you will get significant heat loss when you are storing that thermal energy for a large amount of time in any medium, whether it's a phase change medium or a latent heat based medium. Okay, the rate of heat loss may be modeled as Q dot loss, which is joules per second, which is watts, equals to H into A into T minus T ambient, where H is the heat transfer coefficient, watt per meter square Kelvin, the amount of heat lost per unit time per unit meter square of the exposed surface for a given Kelvin of temperature gradient. Okay, so that is H, the heat transfer coefficient. A is the outer surface area of the storage unit, and T minus T ambient is the total temperature gradient between the stored medium and that atmosphere. So for example, if you look at this system, suppose you have a sensible energy storage system. Okay, so some sort of a high density brick system, right? This is at a certain temperature T, which is changing with time as it is losing heat to the external environment. The total volume of this packed dense hot material is V. Okay, this is surrounded by an insulator concentric insulator layer, and the outer surface of this insulated layer is A, the outer surface area. Okay, so heat is being transferred from the interior of this brick system, hot brick system, to the outer ambient at a heat flux Q dot, and H is the heat transfer coefficient between the storage system and the ambient. Okay, so then we can show that the temperature of this medium at any given time is the initial temperature of the medium T0 minus the initial temperature gradient T0 minus T ambient. T0 is the temperature at the beginning of the storage process. Okay, so T0 is when you have charged your high density material and heated it up, and then you are leaving it on. So at that instant, at the moment you are stopping the charging process, that initial temperature is T0. Okay, this is the ambient temperature into 1 minus exponential T, which is time, by a characteristic time parameter tau st. Okay, so this is the temperature at any given time during the storage process equals to initial temperature minus the initial temperature gradient T0 minus T ambient into 1 minus exponential time by the characteristic time TST, tau storage. Okay. Now this tau storage can be expressed as the volume of the storage medium, the V here, into the density of the storage medium into the specific heat of the storage medium by the surface area exposed to the ambient, this A area here, into the heat transfer coefficient H. So we are not deriving this, but we can derive this assuming certain simplistic assumptions that there is no spatial gradient of temperature inside. The temperature on average is changing with time, whereas there is no spatial gradient here. This is a very drastic simplification, but it gives you an overall order of magnitude analysis of the time it takes for the energy storage medium to lose its heat and reach the ambient. Okay. So this is the characteristic time. All right. So one characteristic time is when tau st, tau storage, is 1. So this becomes e to the power 1. I think there is a small mistake here. I will just change this. This will be minus here. Okay. So e to the power minus t by tau st. Okay, so let's see if the ideas match here. At time t equal to 0, this expression becomes e to the power minus 0, which is 1. So 1 minus 1, this entire term drops out. So the temperature at t equal to 0 is the initial temperature T0 as we expect. Okay. Now as t tends to infinity, that is at extremely large times, of course all the heat would have dissipated. So clearly the temperature at t tending to infinity would have been equal to T ambient. So is this happening? So e to the power minus infinity is 0. So 1 minus 0 becomes 1. So this becomes T minus T0 plus T ambient. So the temperature at infinite time approaches T ambient. So this is the correct expression, T0 minus T ambient into 1 minus exponential minus T by tau st. Okay. Then the characteristic time, one characteristic time becomes, this becomes 1 minus e to the power minus 1, that is 1 minus 1 by e. Okay. That is when one characteristic time has passed from the time at which the storage of the heat is happening. Okay. So then this expression will give you how much change in temperature has happened over a given period of time from the point of charging. All right. So here V is the storage volume, C is the specific heat capacity of the storage medium, joules per kg Kelvin, A is the outer area of the storage unit, H is the heat transfer coefficient, and rho is the density. Now usually larger is this characteristic time, slower is the heat loss. So we want to maximize this characteristic time as far as possible. So again, if you have a smaller area, if the cross sectional area is small, the volume of the system is large, the density of the system is large, so you have a high dense system, so the mass of the system is large, the heat capacity of the system is large, and the heat transfer coefficient is low, then you have a larger characteristic time. So we want to design systems which have a small area by volume ratio. If you put the volume here, area by volume ratio is basically the total exposed surface area for a given volume. If we decrease the area by volume ratio, then the characteristic time increases. So we want to design that way. We want to increase the specific energy, specific heat capacity, the density into C, the heat capacity, total heat capacity is density into C, and this we want to increase, and we want to use an insulator to decrease the heat transfer coefficient H. If we do all of these things, then we can decrease the amount of heat loss over a given time for the energy storage material. Okay. Now for latent heat storage, heat loss occurs at a constant temperature and causes part of the storage material to change phase. So in latent heat, there is no decrease in temperature of the storage material. Instead, there is a decrease in mass of the storage material, because suppose you are starting with 100 kg of steam. As heat is lost, part of the steam condenses back into water, and that part, condensed part, no longer takes part in the heat transfer process. So you are basically losing mass, effective mass of your storage material. Okay. So that amount of converted mass is no longer available for phase change during the actual heat transfer process. So in sensible heat, you are losing temperature, and in latent heat storage systems, you are losing useful mass. And the amount of mass loss can be given by, again, the heat transfer coefficient H into the outer cross-sectional area into the total time elapsed between the initial time and the final time at which you are measuring the mass loss into T minus T ambient, the temperature of condensation or temperature of solidification, that temperature of phase change minus the ambient temperature, which is the effective temperature gradient, by L. Where L is the latent heat capacity of the system. Okay. So here L is the amount of heat that is being absorbed or released during the phase change process per kg of the material. So when we discussed previously these values of latent heat, this is the L that we are talking about. How much, in terms of mass usually, how much is the latent heat present per kg of the phase change material. Okay. So that is the L here. Okay. So once again, the mass loss will be minimized if the latent heat capacity increases. So that usually does not happen, because unless you change the material itself. It will also decrease if H is decreased. So your heat transfer coefficient is low. So you are adding insulators to the system, and you are decreasing the total exposed area of the system. That is also important. So those two things if you do, then you are losing less amount of mass to heat loss. Low values of H, small exposed area A. So this is also a typo here. Small exposed area A per unit volume are required to reduce heat losses. Okay. Even then, thermal storage units can only store heat for 10 to 12 hours maximum without significant losses. Okay. So the total period of time for which heat can be stored in thermal storage units is maximum 10 to 12 hours before the losses become significant enough that it no longer becomes economical. Hence, they are good for diurnal cycles. So like day-night cycles of solar power plants, daily changes in energy demand, etc., and not for seasonal cycles, summer to winter. So you cannot store the excess heat that is present in a summer day and use that to heat up your buildings on a winter day that is 6 months later. Because our heat insulation systems are not good enough to store heat for that period of time. It can only do that for half a day at most. So 10 to 12 hours maximum. Okay. So we will stop here. In the next class, we will discuss the storage of coolness, which is the last part of the thermal energy storage systems. So thank you for listening and have a good time, and we will see you in the next class.